Yet.
Yet. All right, well, thank you very much for coming. Apologize for lack of seats. But there are a couple here. I'm not going to be saying. Is anybody here a fire marshal? Okay. I actually have a lot to get through, and there's going to be a lot showing up on the screen. I'm going to be asking you to read a little bit too. So if you can't see from the back, you might want to scoot up a little. I usually have a little less text on presentations, but there's going to be quite a lot because there's a lot of information to get through. First of all, I want to acknowledge Phil Wyden, just passed away. This was a few days ago. He really started, maybe not started, but he really brought the Tuscan Formation, which we all know and love, to the forefront of in Chico. He was a professor at Chico State for 21 years, retired in 1989, but I challenge anybody to find a better paper, a more up-to-date paper on the Tuscan Formation than the 1969 version of Phil Wyden's Tuscan Formation article. So he was truly the king of the Tuscan, and we lost an important figure a few days ago. Okay, so what I'm going to talk about, Phil Wyden, I don't know what his opinion was on fracking, and it's completely unrelated, but what I'm going to be talking about is kind of divided into 4 parts. The first introduction part is why should we care about hydraulic fracturing? And some of you have a lot of experience with this, others you don't. So I need to start with that content. And then where and how much is it occurring in California? Let's get real about California. I am going to cover areas like Pennsylvania and Texas and Wyoming, but this is going to be California-centric for the next hour. Part 2 is going to be what are the mechanics of hydraulic fracturing? I mean, we have to know what does hydraulic fracturing mean? What does it mean to frack a well and to horizontally drill a well? We could say it's evil, but we need to know what is evil. We need to define it. We need to know what the practices are. That's not what I'm saying, but for any of you that have opinions about fracking, you have to know what it is. Okay, so we're going to talk about that process, what's in the fluids itself, and how much water is used in hydraulic fracturing. And then the major part is going to be the contamination risks, which is what the title of the talk really is. But what are the contamination risks on water resources, the impacts of methane leakage from wells, how important is well integrity, and what are the risks associated with the water that's produced in hydraulically fractured wells. And then what's the latest issues going on with California? And there are issues going on right now that have shown up in the press with California. And then I'll conclude with some of the major studies. I'm not going to spend much time on this. I'm just going to direct your attention to what those are. Okay, so why should we care about hydraulic fracturing? Well, when you look at total gas produced in the United States since 1940 to 2012, I think this data came from, or even you look at this flatlining in the green, which is just normal gas withdrawals. But if you start looking at this curve right here, since around 2005 or 6, this curve has shot up in the amount of production of gas wells in the United States. It's significant. You're not going to really find a steeper slope than this on any of these. This is fast and furious. And it's not just with gas. Well, let me talk a little bit about gas before I get to oil. And this idea that we're fracking gas in these unconventional resources, and I'll describe that in a minute. But before we get to that, production of natural gas has increased by more than 30% in the last decade. That's an enormous amount. That's acceleration. And when you look at from 2002 to 2013 or so, these are all just shale plays throughout the U.S. And it's pretty flatline until you get to this point. And that's where all these things you've heard about Barnett and about the Marcellus, where they've just taken off in 1 million cubic meters per day. So when people tell you that we've been fracking for decades, since the 1940s, they're right. But this hasn't occurred until the last decade or so. Okay, that's what's important. In Pennsylvania alone, and throughout this talk, I'm going to try to give you a lot of numbers, a lot of scale. We got to get our scale straight here. In Pennsylvania alone, 7,200 shale gas wells were drilled in the Marcellus Formation, in addition to the 34,000 wells that are there. That's just 2012. Let's go to oil. Why should we care about hydraulically fractured wells in oil? Well, again, from 1950 to 2014, look at this. Look at this acceleration of fracked oil right here. That's this is total oil being produced, but that acceleration is due to hydraulic fracturing and horizontal drilling. So if you look now at the formations and the plays around the United States, what's taking off in the last 5-6 years? Well, let's look at the Bakken in North Dakota, and we look at the Eagle Ford in Texas. These things are hugely expanding. And have they peaked? I don't know, but they're expanding, they're accelerating, it's huge. And why have they done that? It's hydraulic fracturing and horizontal drilling. If you look at the Monterey Formation, it's not changing at any scale. It's just not changing. That could change, but it hasn't changed yet. All right, I'll get into that too. So, map of oil and gas shale plays in U.S. and Canada. I'm going to be referring to examples in Marcellus, which covers a lot of Pennsylvania, West Virginia, down in here. I'm going to be talking a little bit about the Barnett, which is down in here. I'm going to be talking a little bit about the Bakken, which is in North Dakota, which is here. And then, again, California. Not a lot of brown spots in California, but there is the Monterey system right through here that I'll talk a little bit about. All right, so if we look at the consequence of this, power generation is supposed to grow by natural gas 60% in the U.S. over the next quarter century at the expense of coal. Approvals for liquid natural gas export terminals are already on the way. They are going. These are LNG, liquid natural gas terminals. We're becoming a gas exporter. And we're doing it by the TCF, by the trillion cubic feet. And these are multi-billion, tens of billions of dollars installations that are all dependent on getting this natural gas to another market. That's how much gas is being produced right now. The impacts of increased shale oil. Well, at current price is about $50 an oil. The estimated global, or what I should say, the increase in global shale oil reserves, is a lot of money. So we're talking about trillions of dollars. We're talking about a lot of attention paid towards this. So given the economic value of these, there's going to be there's certainly going to be some exploitation, even more of these types of resources. So we better get on board with what it is and what we're dealing with. All right. So again, where is hydraulic fracturing occurring? Well, if I just go from this chart to here, no surprise, when you look at the hydraulically fractured wells per county, and this is just in 1 year, per county, if you look at the yellows and the greens, those are 500 to 2,300 fracked wells in 1 year per county. And you see all these deep colors through here and through here and through here and through here. It is widespread. And there's some over here in Kern, which is a huge aerially it's a huge county, so it covers a big area. And I'll talk a lot about what's going on in Kern County with regards to hydraulic fracture. So what are the concerns with all this? Well, obviously, we talked a lot about the water resource concerns. There's surface spills. There's wastewater disposal. I'll define that later. The term wastewater is used a lot, but it's really just the water that's produced or flows back after the hydraulic fracture. And then the drinking water contamination through poor well integrity. That's huge in hydraulic fracturing. How well are the wells constructed? Where are the leakage points? That's really key in in trying to protect water resources. There's increase in volatile organic compounds and air toxins that are potential threats. And I'd say this is probably even the biggest threat right now to scientists. There's huge data gaps. There's virtually no information in California about flowback produced waters in terms of the chemistries of them, how they've changed over the years. There's almost no information. And so the data gaps are probably your biggest hindrance, scientists' biggest hindrance in trying to prove or show or investigate. And then, of course, the 2005 Energy Policy Act that we all have heard of, that exempt a lot of hydraulic fracturing fluids. That's changing a lot right now by state. But, and that brings me to the final point here, is environmental oversight is not really a federal issue. It's actually oil and gas. It's highly variable around the country, and it's really monitored by state. So Texas and Pennsylvania are going to have different regulations than Wyoming, than California, and Wyoming and so forth. All right, we got to talk California here. So this is California's oil and gas fields. Gas in red, oil in green. That's a lot of oil and gas fields. Let's talk about the oil and gas production in California. It is a $34 billion annual industry, employs lots of people. It's the third largest oil producing state in the nation, 500,000 barrels per day. Lots of property tax payments to the state, $800 million annually. 90,000 active or idle production and injection wells in California. 90,000. Holy cow. And that's just a production idle or active. That does not include the abandoned wells. Injection wells have been an integral part, right? And injection wells are key to understanding California's oil and gas industry. I'll explain this more later, but injection wells are what allows that 500,000 barrels to be produced per day. You're injecting steam, injecting water into the reservoir, pushing the heavy oil to the producing wells. That takes a lot of water. Okay, injection wells are used to increase oil recovery. 75% of California's oil production is the result of these injection methods. So when you talk about injection wells, we're talking about a lot of California's 500,000 barrels. Why am I focusing on injection wells? That's how you, most companies, that's how you try to get rid of the flowback and produced waters from hydraulic fracturing. So injection wells are called Class 2 injection wells. That's the main method to get rid of flowback and produced waters from hydraulic fracturing. So I'll talk about what California does in terms of injecting or getting rid of their flowback and produced waters. But we should look at that in terms of really the amount of injection wells that are already here in California. All right, if you look at California's oil production in barrels, we've peaked in the 70s. We're down. There is no Monterey Formation extravaganza. That does not exist right now. It might exist later, but it doesn't exist now. That's what California's been looking at the last few decades in oil. Again, if you look now from the 81 to 2012, when I just look at this, I see that, whoop, and I see that. That is Texas oil, and that is North Dakota oil. That's Eagle Ford production, and that is Bakken production. Those are oil shales. California is in purple. There's really nothing there in terms of the latest thing that's going on. But we're interested in California. We want to know about California. If you look at California's oil basins or sedimentary basins here, there's the San Joaquin, there's the Sacramento. Most of the oil production is going on in the southern San Joaquin here, but there is some in the Los Angeles Basin through here, and the Salinas, right? The Salinas Basin, there's Monterey Bay right through there. So there's some here, but most of it's going on in the southern San Joaquin. All right. one of my major points here is California is different. We hear a lot about fracking, a lot about the expansion of oil and natural gas. California is different. The reservoirs in California that are produced using those reservoirs in California are not as laterally extensive. So the ones that are fracked in California are not as laterally extensive. And therefore, they don't use as much water as other places. And they use different chemicals. The initial permeability in California of reservoirs is much higher, meaning you need very low permeability shales for fracking to work. You need low permeability sands for fracking to work. We don't have a lot of those. In fact, we don't have much that are economic. Hydraulic fractures tend to use less water, I mentioned that. And they tend to have higher, because of less water, there are slightly higher chemical concentrations, just because of the less water. The wells tend to be shallower in California than in other places, and more vertical. The horizontal wells that we hear about the 2 kilometer long horizontal wells, they don't exist so much in California. So, California's different. That doesn't say hydraulic fracturing doesn't occur in California. It sure does. About 150 fracked wells per month. 100 to 150 per month. It occurs here, but it's different than what we hear in the news. So where and how much is occurring in California? 85% of the fracturing occurs in these fields. All of them are in Kern County. North and South Bell Ridge, Lost Hills, Elk Hills, southwestern portion of San Joaquin Valley. That's where most of the fracking is going on in California right now, those 150 wells per month. From 2013 to 2014, that's basically 1 year of data. There's about 100 to 150 a month. For comparison, there's over 1 million hydraulic fracturing operations throughout the U.S. 100,000 of these seem to have been recent years. California is a pretty small portion because they do not resemble the low permeability, extensive, continuous shale layers of other places around the country. Here's frackfocus.org, which I'll just explain a little bit. Their data. Now, frackfocus.org didn't get going until 2011. So that's why this data is just from 2011 to 2014. And if you looked at the number of hydraulically fractured operations voluntarily put in per month, it varies from about 80 to there's 130. Now this is just from a few of the sources. When you include, here's some information about Frack Focus. It is kind of the site to go to look for chemical compositions of frac fluids and the types and amounts of fracking going on. But going back to here, the average was 68, but that's just from Frack Focus's voluntarily given notices of fracking. There's probably a lot more than 68 going on, and the study by the California Science and Technology Committee bumped this to about 100 to 150 a month based on the word frack showing up in well notices to the Department of Oil and Gas Geothermal Resources. So there's a number of ways to try to get this data. Frack Focus is just one. But 4% of the total nationally is probably what's going on in California. If we look at that, about 150, now this includes not just what Frack Focus says, but well stimulation notices. There's about that much. A lot of people ask about acid fracturing. We're looking at 0.2 per month, 0.2 in 0.01 per month of matrix acidizing. There's very little acid fracking and matrix acidizing that occurs in California. That means you're putting in hydrochloric acid, hydrofluoric acid. You want to dissolve some of the rock in order to increase the flow. It mainly is effective in carbonate reservoirs. We don't have those in California. So there's not a lot of acid type fracturing that goes on in California. So again, 96% of all fracking occurs in Kern County. If you look at the, just in California, annual average production well records with frack indicating in the well records, this is between those 4 years, 2002, 2006, these 4 years, 07 to 11, and these last 2 years. So this is per year. You're seeing about 500 to 700 wells per year in California. And all of them, almost all of them, sorry, 96% is Kern County. And 85% of those are in those 4 fields, which I talked about before. All right. And it's been estimated that hydraulic fracturing has facilitated about 20% of oil and gas in 2001. What does that mean? Well, when you look at the production in California oil and gas, how much of that is due to fracking? About 20%. Most of it is due to this injection of steam and water to move the heavy oil, which is not related to fracking. All right, we also care about what's going on close to us. This is the Sacramento Valley. These are the gas fields in Butte, Glen, Colusa, and Sutter. These are the wells that are active right now. And the blue, we might want to get a light on actually, the blue, or light off. The blue right here, those are the fracked wells nearby. There's Sutter Buttes. So there's some fracking going on here. There's a little fracking going on in Glen. No fracking in Butte. Again, now, if we just looked at the reports that are in Frack Focus, those are the wells being hydraulically fractured there. There's one in Glen. But if we look at Butte County, for those who are curious, there's, we're talking very few wells in Butte County. Most of them are for gas storage. Very few of the wells, of the 32 wells, are actually in production. And none of them have been fracked, according to Frack Focus, in Butte County. So yeah, no wells have been fracked in Butte County. And if you look at Butte County gas, actually, it's almost went down to nothing since 2000. So it just gives you some reference of what's going on locally. In Glen, it's a little different. One well hydraulically fractured on June 2011 since Frack Focus has come around. Okay, so what is hydraulic fracturing? Finally, we're down to 20 minutes. We're down 20 minutes. We're not finally. What is? Well, what is hydraulic fracturing and horizontal drilling? Well, drilling's down vertically. You go down, but then you can actually go laterally up to 2 kilometers and more. 2 to 3 kilometers, you can drill horizontally. And you can track formations, and horizontal formations, as thin as about 100 feet. It's pretty remarkable that of the technology. But after horizontal drilling, the well's hydraulically fracked, used for anywhere from less than 1 million gallons to 20 million gallons of water per well, with chemicals and proppant, to bring the formations up to 10 to 20,000 psi. That's fracking. The fractures are induced by the high pressure, the high volume and the high pressure of the frac fluid. And that's what you actually overcome the tensile strength of the shale. It cracks, and the proppant goes right into those cracks and props it open. And then you recover that fluid back. I want to go over that process because it is very different in what goes on again in California in fracking than in other parts of the country. Other definitions of fracking, there's the engineering definition of the exact process of fracturing that well. That's the engineering definition. A lot of other people think it is different. Fracking is drilling. Fracking is putting the casing in and cementing. Fracking is fracking. Fracking is getting the water back. Fracking is dealing with the water when you get it back. It's all fracking. So there are other definitions, but really the precise definition is the act of cracking the formation. And really, it's the pressure. When you talk about fracking, you're talking about pressure overcomes the tensile strength of the rock, causing those fractures. I think we got a good idea of that. So this is a kind of a simplified cross-section of what goes on in oil and gas fields. most of the conventional oil and gas fields are on these what are called traps. So this is kind of a folded layers here that traps the fluids. As they migrate from a source rock, they will trap up here if there's some impermeable layer above it. So you can get gas and oil and then water. Fracking, and what we know about, is going on down here in the Marcellus, in North Dakota, and just about everywhere else in the country where there's these shales. And these shales are down in here. They're in the deeper parts, and look how laterally continuous they are. That's where what is known as the kitchen. You have to heat up organic matter in an oven, basically, nature's oven, and that's how you create the oil and gas. And then instead of it migrating out, in some cases, it stays there. It can't get out. So you go down here and you frack and drill horizontally to get that oil and gas. So this is unconventional. This is conventional. When we talk about horizontal drilling and fracking, we're talking unconventional. Eagle Ford Shale in Texas, typical example. Going down here is our vertical well. That's a typical vertical well, but you can go down 3 kilometers and then over 1.5 kilometers into this very, very thin 80-meter zone. And you can steer that wellbore all the way in. And that's what this is showing as well. In California, it's different. We frack shallow in California. We frack more wells that are, they look conventional, but there's heavy oil or there's very brittle formations that could get fracked. But it's very different than these long horizontal fracked wells that happen in other parts of the country. Now, if you look at the scale of where the actual oil and gas is, that's 10 microns there for scale. This is a backscatter image. It's that's probably a tenth, a hundredth of a millimeter. So there's 1,000 microns in a millimeter. So that's 100th of a millimeter from there to there. And this kerogen is just another word for where most of the organic matter is. And it's very small pores where this methane and bigger hydrogen compounds are hanging out. And the idea is to try to fracture this stuff to give them pathways out that aren't there naturally. Here's another idea for what we're talking about. There's 50 microns, so again, probably close to 100th of a millimeter. And if you took just a little square of there, and you blow that up, now we're talking a half a micron, that's a 500 nanometers. And you look at some of these pores here and some of the organic matter there, that's what they're trying to access. Getting that stuff, getting it micro-fractured enough so you can get this organic matter, or get this gas and oil into an artificial fracture system to get that to the wellbore. By the way, that's about a human hair for scale relative to this. Those are the same scales there. So here we are drilling this vertical well to a horizontal well. And I want to talk a little bit about the process of this casing, because that's where the groundwater is. This casing process is critical, and probably the most important aspect in contamination of groundwater dealing with fracking is what goes on, not down here, but what goes on here. And that's what it's kind of opposite of what you'd expect. It's like, well, that's where all the fracking, that's what all the stuff is. Well, it's actually what's going on in this casing and what's going on the surface when they deal with this flowback water. That's probably the biggest threat. So this is this is a bit that they use to drill down vertically and then horizontally. Some people are wondering, how can they drill horizontally? Well, you have the motor that's spinning this thing right here. So that's what's spinning it. And you're able to push on certain parts of the wellbore to make it deviate 3 to 8, sometimes 18 degrees you can deviate per 100 feet. So if you're going down, not vertically, you're actually deviating 18 degrees per 100 feet of vertical distance. So first you put in when you drill, the first thing you do is you put in this very shallow conductor casing, it's called, and maybe down to 100 feet. It just isolates your well from the really kind of loosely consolidated sediment at the surface. Then you put in something called the surface casing. So not this outer ring, but the next inner ring. And that surface casing is just it's a pipe that you put down, PVC pipe, sometimes steel, that you can then, you put that in maybe down 100 feet below the groundwater, or it's different for different states. I'm sorry, the aquifer. It's different for different states and how far that surface casing goes. And then you pump up cement, and then that cement comes in and cements the surface casing to the conductor casing. So you have a pipe, then you have cement, and then another pipe. You then go down to deeper wells and do an intermediate casing. Same thing, put the case piping in. When you're down to a certain depth, you go down, you cement it, you create another layer of cement. And then you go down and do it also for production casing as well when you get down to the deeper depth. So when it's finally done, you're looking at something like this in cross section. You got conductor casing, surface casing, intermediate, and production casing. And each one of these, this pattern here is cement. Seems like a lot of protection up here, if everything goes well. A number of problems can occur. If the mixing of cement, if you're mixing the cement and the actual drilling mud that you're using, that's a problem. If your casing that you're putting in is off-center, doesn't go straight down, that's a problem. And especially with gas migration, if you're having problems with the cement mix and how it cures, that's a problem. You can create cracks. Any of these can lead to problems that can lead to leakage, specifically with gas. Okay, so once you get the casing goes, then you do what's known as perforation. You actually stick a charge down there and you blow through the casing, or sometimes just the rock that's down there, to create holes. This is accessing the formation. And once you do that, you now have access to formation, and the oil and gas and water can come in and up through this inner tube. So what happens when you hydraulically fracture a well? This is a nice cartoon of all the equipment that's there for hydraulic fractured wells. You have sand trucks for the proppant. There's the wellhead. You have blenders. You have storage tanks. You have pumpers. You have a data monitoring truck. What does it really look like? Kind of like that. This is a typical well in Pennsylvania for the Marcellus. 5,000 foot well using 5 million gallons. This is not California. This is Pennsylvania. Getting up to 10,000 PSI. 18 megawatts, basically creating lots of power in these various stages. I'll describe what that is. And for fracking a well, maybe 1 to 2 days, maybe 3 days. That's a lot of equipment. On the high end, you're getting up to 15,000 PSI, and you're injecting almost 100 barrels per minute. Here's some of the equipment I just described that are there. Now here's what happens when you actually frack a well. And you do this in multiple stages. If you can get maybe one of the lights, that would be good. There we go. Here's what happens when you frack a well. You're, what you want to do is, once you've drilled horizontally, you've done all that, done your casing, what you want to do is isolate only a certain part of that horizontal leg or stage. So you put in a, let's say right here, this is only one part that you want to isolate. So you put in right here, this clogs the well, so you're not accessing any of this stuff. So you block that off, that plug, and then you bring in your perforating gun and you shoot the clusters. So these are clusters of shots that are shooting here, then you shoot another one there, and another one there. And you do that about 6 or 7 times to create one stage. And then you take this out, and then you start pumping in the high pressure fluids. What's originally called a pad You actually pump in the high pressure fluids, it goes in, and there's no proppant. It's just the chemical mixture. It goes in, you build up pressure, and then you add the proppant. And then that goes in, you gotta time that perfectly, so when the pressure gets just to the right spot where to crack it, the proppant's right there to go in. You then start to, you then pump in more of the fluid without the proppant in, that's called the overflush. And then when you're finally done, you release the pressure slowly and you flow back the stuff. So there's 4 parts to this. The pad, the proppant, the flush, and the flow back. And this flow back can go on for a long time, weeks, months, even the whole life of the well. So I'm not going to go over that part, but I'll go to, let me do one more, fracture heights. And a lot of people are worried about when you make these fractures, how high do these things go? And there's a lot of data for this, tremendous amounts of data for this. So they typically go tens of hundreds of feet high. Probably the biggest one is 2,000 feet. That's very uncommon, but it has been 2,000 feet vertically. And I think there it is, 1,900, but very low probability of that happening. Here's the crazy thing in California, up to 3% of fracked wells are shallower than 2,000 feet. That's quite a few, that's tens of wells that are fractured in a pretty shallow zone. So tens of shallow wells being fracked per year in California. And if you look at the data from the fracturing depth, there's feet there, and there's meters there. Quite a few of the fractured wells, these are just from different data sources, are in this shallow zone in California. That's not typical of other parts of the country. But again, we're not doing big horizontal drilling, a little bit, not big. And if you look at the amount of the depth of these fracked wells in meters and in feet, the shallow wells are really in this red and orange. You get an idea where all the shallow fracking is going on. And we're really concerned about this because there are TDS, there are total dissolved solids in the waters, in these low TDS values. This is what drinking water, and this is the upper value of drinking water. And there's fracking going on near these aquifers. Some are going on in this really high TDS. Notice how 10,000, that's the limit. Once you get beyond 10,000, it's not really, it's considered unprotected, I guess, by the Federal Safe Drinking Water Act. So what's in this hydraulic fracture fluid? Well, toxicity warrants further review. A third of the chemicals used in hydraulically fractured fluids, people don't know anything about with regards to toxicity. Most of the fracked fluids are not considered highly toxic. In fact, almost the most majority are not considered toxic. But let's just look at the ones that are. So again, about a third of the chemicals in California fracked fluids, there is no information about their toxicity. A few of them evaluated by plant, how they react to animals or plants, but all the data that we do have for toxicity is relative to mammals, and it's not long-term. It's kind of short-term, and it's relative to mammals only. And that's not including the third of the chemicals that we don't have any information. So let's just look at what's in fracked fluid. 67 to 99% is usually fresh water. Proppant, 1 to 11%. That's either sand. And then there's all these other things. And you want to ask yourself, why are these other things in here? Well, there are these friction reducers that want to reduce the friction in the fluid to allow that sand to flow down into the wellbore. You can imagine that there's going to be a lot of friction with all that sand at high pressures. You have to reduce that friction in some cases. There's biocides, disinfectants, because you can get bacteria growing, because you're putting a lot of either sulfuric compounds or other organic compounds in there. There's surfactants to bring down the surface tension. There's thickeners. You know, you won't want just water when you frack. You want it to be thick because you want to hold up that proppant. If you just have water in there, its proppant's all going to go down to the bottom of the well. You don't want that. And then there's these scale inhibitors, meaning you don't want your well to get precipitants on the edge of it, or on the sides of it. And then acids. So, here's a slick water frac, and I'll explain what that is from Colorado. Most of this is water, 96% is water. The black part is proppant, and then that's the other stuff. Surfactant, the friction reducers, the acids. This is from Utah. Most of it, 87% is water. There's proppant. There's the surfactant, the cross-linked gels, and so forth. So you kind of get an idea for the relative percent of these chemicals in there. Well, there's two types of main frac fluids, and California uses this type, cross-linked gel. It looks like that. It's kind of nasty looking, but it says guar. I shouldn't say just guar. It's called guar, and it's 10 to 100 or 1,000 times more viscous than water. But here's the thing: is that it doesn't allow lots of turbulence. This is a Reynolds number for those people that like Reynolds numbers. This is the relative turbulence of when this is flowing in your well. It keeps turbulence down. It's thick. It's viscous. And that's what holds up a lot of the proppant. So it's got excellent proppant transport. Now the opposite of that is slick water. Slick water reduces the friction. So therefore you can pump lots and lots of water in this, high pumping rates, relatively fast, to keep the turbulence really high. So in there, the turbulence keeps the proppant going. Not the thickness, but the turbulence. And that's what creates, that's why slick waters are so nice, because they create a certain kind of fracture, very complex fracture network, whereas these guys create a very simple fracture network. This is used in California. These are used a lot in other places. And it's the main reason why Pennsylvania, West Virginia, North Dakota, why they use a lot of water in their fracking, and we don't. This is the main reason. They use slick water fracks. Slick water uses lots of water to keep that turbulence going, to create that complex fracture network like this. Whereas California uses a lot of these cross-linked gels in order to create those types of fractures. Other types of things that are in frac fluids, you have these oxidizers that once the fracking happens, you want to get that junk out of there. You want to oxidize it. But they have this time release coating, because you don't want it to oxidize at the wrong time. So there's all sorts of engineering that goes on in frac fluids. But here's that mammalian toxicity of well stimulation technology that's fracking chemicals. Insufficient data, 33%. The less toxic stuff is here, and there's a significant amount in this more toxic stuff. And that's just the what to know. All right, we're going to go over every one of these. This is what's reported, all these chemicals, and the color coding is red's the highest and blue's the least. So you can get reds and yellows. These are what's been reported in as far as what's in chemicals according to Frac Focus. And these are what's not, these don't have any information on, they don't have CASS numbers, but my point is there's a lot of stuff in this. There's a lot of stuff in this. And then even the EPA study looked at all these are chemicals known as suspected carcinogens under the Safe Water Drinking Act. They're in here. And then finally, the most common ones showing up in fracking fluids are these. So again, most of them are non-toxic. There's a lot of information though that is not there. And only oral toxicity is really talked about. What about the environmental impacts? What about plants? What about ecosystems? What about other living things besides mammals? No information. There's a little bit on crustaceans, believe it or not, how they affect that, but no other information. Chronic exposures, nothing. Time dependent, nothing. Okay, fracturing fluid flow back. Once you've fractured, you want to get that water back. And this is days from the hydraulic fracturing event. This is the TDS, and then this is the average flow in the interval. So the TDS here, we're looking at is in, yes, is this color. Remember I said the drinking water is like 10,000 and less in TDS? Look at these values of TDS for flow back. 100,000, 150,000. This is a Marcellus flow. And it just goes on and on. That's crazy. That's a lot of dissolved solids. And if you look at the average flow, it's still going. It's the average flow back water is up here, but then it decreases. But it goes for quite a ways. 2 to 3 weeks, you're still getting this stuff back. So again, flow back water is the stuff that happens just after fracking. Produced water is the stuff that happens weeks and weeks and weeks as you go. How much of this do you get back though? When you put frac water in, you typically get maybe 9 to 53% back. Where does all the other stuff go? And the stuff they do get back, we'll talk about later, but they reuse. So the stuff that's in flowback produced waters, you have all sorts of new compounds that could form between the chemical reactions. You have dissolved substances from all these reactions from the fluids. There's all sorts of things that can be in this flowback produced fluids. All sorts of compounds contributing to those high TDS values. And that's why I think what you do with this stuff is probably the most important aspect of hydraulic fracturing. Is what do you do with this? It's very different than the stuff you put in. And by the way, there's no information in California about the chemistry of flowback waters and how they change through time.
Why? Why?
Has it not been regulated? Hasn't been regulated.
Okay,
and
they just won't tell anybody. Right.
And the comparison of produced waters from unconventional, you can see some of these Bakken and Marcellus, that's unconventional. Look at these TDS values, they're huge. And that's produced waters, by the way. All right, I want to stop right here and say, I got a lot to talk about. And there's more to go. And it's unfair for me to keep you here for longer than an hour. I know I have 10 minutes left, and I want to answer questions. I'm at to the point now where I want to get into the specific studies that have looked at flowback water, stray gas contamination, and treatment facility contamination due to fracking. None of these studies are in California. There's only one study that's been done in California, in the Inglewood field, and it's controversial, and there's not a lot of data that has to do with arsenic. So I want to give you the opportunity to leave in 10 minutes if you'd like. But I think there's going to be maybe a few that want to understand, I want to know these studies as well. So I'm going to go for another 10 minutes. I'll stop. I'll give you a chance to leave, and then we'll ask questions. Yeah.
Just real quick, what about, thank you, it's excellent so far. What about outside the U.S., though? Is there any environmental studies that have been done on the flowback water?
That's funny you say that. I'm right here, right there.
Oh. Huh.
It's not, a deep injection of wastewater is not permitted in Europe, unless it's for enhanced oil and gas. Yeah?
Well, one thing, of course, on my mind is if you're drilling horizontally, how much loss do you get into active faults or fault zones?
Yeah. So,
vertical faults.
if I get into the whole seismic part of this, it would expand the talk even more. The injection is the biggest issue when you deal with seismicity problems with fracking. It's not the process of fracking itself. It's a very, very small amount of energy they're putting in to create earthquakes. It does create an earthquake, but it's tiny. But when you get flowback water, class 2 injection wells, especially in places like Ohio, where a lot of the Marcellus water goes into, you create earthquakes. So yes, earthquakes are an issue with injection. That's why this is I think the most important part of fracking. What are you going to do with it?
But what about contamination of, let's say, shallower aquifers if you have movement of, let's say, a fault?
Yeah. If you're, and so that goes back to the information that's out there, the studies that are being done. The EPA is putting together their final aspects of their huge report on hydraulic fracture. One of their studies has exactly to do with that. What is the probability of natural faults being migration conduits of fracking fluid to aquifers? Basically, the preliminary results say there's very little danger of that in places like the Marcellus, places like the Bakken, when the hydraulic fracturing is so deep relative to the aquifers. But when you get into shallow water fracking, that's an issue. You know, fractures in shallower zones, they don't want to go vertical, they want to go horizontal. So when you fracture a shallower zone, they're not going to go propagate up to your water zone. It's going to go horizontal. In the deeper ones, they will go horizontal. They will go vertical. Yes?
So maybe you explained this already, but I couldn't understand. You said fracking has been going on for the last 10 years when you see the inflection, you see the exponential increase.
Yes.
Why?
It's engineering. It's what's that? Oh, sorry. The question is why is fracking picked up in the last 20 years, 15 years? It's engineering. It's the same thing for almost any kind of oil and gas exploration. This is one. It's engineering. They figured out how to do it.
They figured out how to do it,
and the infrastructure's there.
And there's no regulation making it expensive.
Right. I mean, you saw the regulations are here and they're coming even more and more. But it's engineering is a simple question. It's a simple answer to that. They figured out how to do it at super high pressures, and they're getting the chemicals honed in, but I tell you, there's got to be a series of factors in place for any kind of large-scale hydraulic fracturing to work. You have to have an infrastructure that is ready to take the gas or oil somewhere else. You have to have rights for the surface water. And the land. It takes a lot of land to do this stuff. You got to have a ton of capital expense up front. You don't make money for quite a ways because each well isn't that great. It's hundreds of wells, it's thousands of wells that make you the money. And that's what they're doing. So this is not something to take on by mom and pop companies. These are big these are big projects. Yes?
Yes, please. From my limited understanding, Senate Bill 4, which is supposed to regulate fracking in California, it's supposed to result in an independent study this summer of the environmental impacts of fracking. What I'd like to know is, do you know which group of people is doing this and how extensive their research is likely to be?
Let's see. Don't pay attention to the slide numbers. A lot of them are hidden.
It's not on the video.
Yeah. Don't be scared. Let's see, where was this? Yeah, all right. SB4 requires a study on stimulation. There's a statewide environmental impact report. The draft is already out there, and I've seen some of it. But their main study is coming from. Their main information is coming from the. Let's see. Where is it? Sorry, I'll get there. These guys. This is California Council on Science and Technology, Lawrence Berkeley National Laboratory, and Pacific Institute. And there's a couple of other individuals. This is the majority of where they're getting their information from.
And what is it, you said the draft is already out?
Yeah,
And
draft
what is it
EIR is
saying?
out.
What is it saying?
Well, I have not read the EIR yet, but I have read this. And this is not the EIR, this is one of the studies that was this is the study that was commissioned by SB4. And I have read that. And it was commissioned originally by the BLM and then for SB4 Volume 1. And what I'm going through is that. So what it's saying is what I'm going through. I haven't gotten to the end yet, but that I am going through that. This is SB4's timeline to create this study, well stimulation technologies and their past, present, and future use in California. That's out. That's what I've read. This is coming out later. This environmental impacts, and then selective evaluations and environmental public health risk. And then there's some other findings. So a lot's going to come out later this year. As far as what they found here, it's kind of what I've been saying is there's very little information in California. Fracking is very different what goes on in other parts of the country. Needs to be a heck of a lot more information on flowback waters, but the fracking that goes on in California is less than 5% of what goes on in the country. It's small, and and they make a big deal about it. They say there are no documented studies that link water pollution to hydraulic fracturing. They say that, and they're very clear about that.
Who are they?
These guys, the California Council on Science and Technology.
As it relates to California?
As it relates to California. Now, there are, and I'd love to go over these other studies, but they do say there's nothing.
How's that factor when they shut down the 11 wells down in Kern County because they said they poisoned the aquifers forever?
Right.
Yeah.
That's not a scientific study, and I do have information on that, and that is that happened pretty recently. And so they didn't talk about that, but I do have a little information.
But it was Cal EPA that shut them down, right, for the information that they had.
Well,
on how toxic the stuff was.
The Dogger shut them down, but it was based on that information. So I'd love to continue, but I know people have to leave, but I also want to answer your questions. So what else is digging at you? Yeah.
Todd, in California, are there any regulations about how much water we use for fracking since we're in drought?
No.
Can you repeat the question?
Okay.
Repeat the question.
All right. Is there any regulation of how much water California uses? California doesn't use that much water in fracking. It's pretty small, but it can have small effects in areas, especially in drought. But there is no regulation on that. But there's unless things change, there's not a lot of water resource impacts in California.
You showed a slide
Yeah.
on the gas production of Butte County.
Right.
There's no legend on what that data is. Is it a billion cubic feet or 1,000 or what?
That would be. I think it's. I have that legend on there.
Yeah, I know you showed it, but I don't see any legends.
It's small.
But then the other question is, there's this huge spike right here from 98 to 99.
Yeah.
It's like 450,000 cubic feet or a million cubic feet.
Yeah.
And can you speculate where that spike came from? Because Butte County says that no well permits have been issued in 25 years. And so where would the 400 million cubic feet of gas come from?
Well, I believe that there has been no wells drilled there. Where is that? My basic answer is I don't know. It's small, but I don't know.
There it is.
Thank you.
Sir?
Yeah.
I think that would be MCF.
What is it? MCF?
Yeah, so that's 1,000. MCF is 1,000. All right. Let's.
How many of the fracked fields that are there conventional ones? Meaning, are they going into plays that are deeper, maybe even a different reservoir, but they already have the infrastructure in place?
In California?
Well, or nationally. How much of that spike is driven because they can go to an area that already has infrastructure that is now amenable to deeper fracking?
Yeah, that's what happens in Pennsylvania. That's what happens in the Eagle Ford. That's what happens in the Barnett in Texas. It's very much related to the infrastructure that's already there. Yeah. So what's going on now? What's the big thing in fracking now? It's Eagle Ford in Texas, and also the Utah, in the Vernal area. The Bakken, I think, is starting to slow down a little bit, but Niobrara in Colorado. So please feel free to take off. I want to get into this major study at EPA's done, and we'll keep this casual. So interrupt me with questions if you like. But this is the national study that the final one is probably going to be out within a year. But I've read some of this stuff, and they break up the risks to water into the amount of water used, the chemical mixing that goes on at a frac well, the actual injection, the flow back and produced waters, and then what you do with the waters afterwards. And there are 16 or 20 different research projects that are going on. And I can show you how this is organized, but it is a massive, massive study. And guess how many studies of these are going on in California? 0. Yeah, there's very little in EPA that's going to address California. And for kind of good reason. 95% of the fracking that goes on is outside of California. Okay, so over-extraction of water resources is an issue. Contamination of shallow aquifers. Contamination of by fugitive gases. These are gas leaks. And I'll tell you, this is becoming a big deal in the studies of places where fracking is going on. Isn't the frac fluids? It's what the methane that is produced because of the good at fracking. The methane gets produced. That's a lot of methane, and a lot of that gets leaked. A certain percentage of that is leaked, and if you leak that in the groundwaters, you can have problems. You can have problems with creating high levels of oxidation. You can, which will allow you to release some of the metals in the formation water. You can release arsenic. You can release some other toxic trace metals in it by affecting the oxidation. You don't want your water to explode, but it's not to the fracking fluids. It's to the production of methane leaking through the wells. Radioactive elements is an issue. The Marcellus in Pennsylvania, it has naturally radioactive elements in there that have been measured in treatment plants, actually increase downstream of a treatment plant. But the actual contamination by the hydraulic fracturing fluids is controversial. And that blows my mind because there are hundreds of thousands, if not, hundreds of thousands of frac jobs going on, and there hasn't been the fracturing fluids contaminating the water. Those studies aren't out there. There are no studies out there doing that. That have pre-conditions and post-conditions that are out there in the peer review, and that's one of the things that a lot of these guys make a point of. That's crazy. Yeah.
No studies anywhere or California?
U.S.
Nowhere.
Right. So this is the way EPA breaks it up into how they approach it for all these different aspects of frac. But there are no publicly recorded instances of subsurface release of contamination fluids into water in California as well until recently. that's what John's talking about. There's these 11 aquifers and that we'll get into. But so there's just a lack of studies. There's been very little information on pre-conditions and post-conditions. Yeah.
Todd,
Yes.
you know, Dogger admits that, not admits, their data shows that once you start fracking, like when you first frack a well, like 5% of them leak, and within, I think 20 years, like a really gigantic proportion of them leak, like 50%. And, you know, if that's anywhere near your aquifers, then you're contaminating your aquifers, and that's what's ultimately what's going to come out. And, you know, it'd be so overpowering that
Well, and they show that in Pennsylvania and West Virginia and in other places, but I'll come to that in a second. This is I kind of want to go over 3 classic studies now that are linking fracking activities to pollutants in water. This is one of them. These types of these EDCs in this is Colorado. These endocrine disrupting chemicals. These are they disrupt estrogen and other hormones from doing what they're supposed to be doing, and they have been linked to wells in Garfield County in Colorado. These estrogen and androgen receptor activities. It's a 2014 study. These are all the wells in these dots here, and that's just a small percentage of them actually. You can't show them. And then these X's are where they did their sites, and these are the these EDC compounds. No, that's redundant. These EDCs, that's the reference level. But then when you get to these sites, they jump up huge. These anti-androgenic or anti-estrogenic or estrogenic, these are not good, and those have been linked. There are, at least they claim, close to 100 chemicals in fracking fluids are known or suspected EDCs. And this is a highly, highly densely drilled area in Colorado. Here's the second one. This is in the Barnett Shale. That's Fort Worth and Dallas. You got thousands and thousands and thousands of wells, tens of thousands of wells in a metropolitan area. And you can't show all the wells here. There's 100 kilometers for scale in Texas. And wells with arsenic levels that are greater than 10 micrograms per liter in red. And they revealed that arsenic, selenium, strontium, and TDS exceeding MCLs, these are all in water wells within 3 kilometers of active natural gas. So that's another big one. Yeah.
When you say the longevity of well is on average, you said it could be up to 4 months?
Nah, well, that's when produced waters are coming out. But the longevity of a well producing gas, it's not long, years. It could be 4 or 5 years, it's not long. Conventional wells are much longer. They could be 15 years, they could be more. But that's why you have to drill so many of these things.
And what do they do with wells that are no longer producing?
Well, it depends on the state regulations. But they're required to, if they're done, to abandon them and to plug them.
What's that consist of?
Putting cement in the actual well and shutting it off and plugging it.
Is that a state-by-state regulation?
It is. So when you go to the Barnett, you looked at these distance to nearest gas well from 0 to 70,000 meters. Wow, 70 kilometers. The highest percentage of TDS is near the wells. Highest percentage of arsenic is near the wells, and strontium as well. So that's the second one. The third one is this one in Wyoming called the Pavilion, Wyoming. And this is just a debacle. This is EPA's, one of their study areas. This is a place where they fractured into the same horizons that they're producing their water. It was just stupidity, in my opinion. And of course they're going to find contamination. Of course they're going to find wrongful doing, because they went after gas that's shallow. It's right next to the aquifers. So they're finding all sorts of stuff in there. It doesn't, but what they find in Pavilion is really Pavilion. It doesn't have to do really with these other areas where they frack super deep relative to the aquifers. So you hear a lot about Pavilion, but a lack of vertical separation between fracturing and the drinking water, of course, is going to increase their communication. And I mentioned that one study in Inglewood, 2012, arsenic was looked at the exceeding drinking waters where they, well stimulation operations occurred. But arsenic is naturally present in Southern California, and it wasn't conclusive that the hydraulic fracturing was the cause of it. Now this is the most talked about impact of leakage having to do with hydraulic fracturing, and it's in Pennsylvania and West Virginia. It's the methane. This is what is always brought up. It's the methane. I mentioned this earlier. Methane in groundwaters near hydraulic fracturing operations has conclusively been demonstrated, and it's not a big surprise. You're producing a lot of methane. It's gas. It likes to go wherever. It's looking for the weaknesses. It's going to go. Now there needs to be additional information out there is what these guys say, but let's look at the impact of methane. It first started in 2011, where 68 homes in Marcellus in Pennsylvania were private water wells. They didn't find anything to do with increased TDSs, metals, radioactivity. They didn't find that. That's what blows my mind, is that they're not finding the contaminants from the flowback or from the hydraulic fracturing fluid, even though they're doing tens of thousands of these operations. But they did find lots of methane. So 17 times higher in concentrations for the homes that were closer to wells. They had higher ethane, higher isotopic ratios. And then in came this study a couple years later, looked at more isotopic ratios, and yes, they found methane concentrations were higher within 1 kilometer of Marcellus gas wells. And they conclude that it was casing and cementing issues. John Scott mentioned the percentage that leaks. Well, they also did a study to look at what's the percentage of Marcellus wells that have casing problems, that have, according to their well reports, or some kind of a violation due to their construction, and they came up with the number of 3%. 3% of their wells have problems with leakage. That's a lot of wells when you're looking at tens of thousands of wells.
Question?
Yes.
Given the extremely high pressures,
yes,
in contrast to the usual pressures of without fracking,
sure.
Is there a completely different engineering process in assuring casing integrity and fracking? It was entirely different, or are they using the old technology and maybe it's not a part to speed?
I think the answer to that is they're using the same technology, they just don't do it enough in frac wells. In other words, the technology that they use to look at casing integrity is up to speed, it's fine, it's good, it's basically sonic sound waves that send out and look at the continuity of the cement. The problem is it's not done enough, and it's not mandatory in a lot of states. SB4 is going to make it mandatory, as far as I know, in California, to actually do these tests, to actually look at the quality of the cement jobs after each casing is put in.
But it's the same technology that was used decades ago for low pressure wells.
Well, it's the same technology that's used today in low pressure wells that they use for high pressure wells. So it's not that the technology in fracked wells is lagging when they're looking at the cement. No, the technology is the same. They're not looking at it enough. These tens of thousands of wells. Yeah.
When they pressurize the well, do they pressurize it from the surface, or do they pressurize it For
from the
packers,
surface.
they do.
Yeah, and that's where those 20, 30 trucks are for.
So they don't pack off the region that they're.
No, they pack off, that's why they drill all the way to what they're gonna do, and then their first stage, they'll fracture the very end of it. And then they'll put a packer on that, isolate it, so that's done. And then they'll frack the next stage, and they'll crack that end of that, and they'll pack that off. So they'll work their way backwards. Yeah,
I was curious about that too, with how the you call them fracked plugs.
yeah.
I was curious how those could plug it when it's enough pressure to
I
fracture
know.
it. But,
Pretty crazy.
but you're saying if they go backwards, it wouldn't even matter if they actually fracture it again.
Yeah, I wouldn't really fracture. But they want control. That's the main thing in this technology. They want control. And if they can isolate a smaller zone to frack, they will have really good control of where those fractures go. If you do it as a big area, they don't have as much control. And that's why in California, they only do 1 to 2 stages of fracking. In Pennsylvania, in North Dakota, Texas, 6 to 7 stages. You know, they'd love to do more than that if it was economical, because you get excellent control of the pressure.
Did you express the length of the stage in which they perforate it? How
Yeah.
long?
Each stage can be 200 feet.
100 feet.
And then another stage, and then another stage. So anyway, this methane has been, not only has it been it's been typed to wells that are close to water wells, but it's been thermogenic, meaning this gas, this methane gas, is not from critters making the gas. It's actually from and in this case, what they determined was from the Marcellus. And this is using helium isotopes that are a good signature for the Marcellus as opposed to these other formations. And you know, when you look at this diagram of the casing here, you know, why would you get this? Well, all the fracking is going on way down here, but if you have problems with the casing in here as it's coming through, you could have these methane leaking through and getting into some of the aquifers. Again, it's not the fracking fluid itself. Someone might ask, well, if the methane's getting in, that's gas. Are the fracking fluids next? They just haven't happened yet? You know, they're going to come up, but you know, gravity, separation, you know, gas is going to go up, fluids are going to go down. I don't know. But these guys were looking for the TDS changes. They were looking for the radioactivity. They were looking for the arsenic. They were looking for the selenium, strontium, whatever, and they didn't find it in the water wells. But maybe it's a matter of time. I don't know. Now there is another, like this guy, or actually woman, Boyer in 2011 that said, no, we didn't find any influence. We didn't find any methane. So when you talk about methane in Pennsylvania, there's the state, I think this is a state-driven study. They said no. So these are, you know, some of the mechanisms for well leakage. A lot of it has to do with the cement fractures. And the EPA is studying this. They're doing all sorts of computer models and how to track this and how to look at the mechanisms and how the well fracture can leak methane. But I want to conclude with one more for the California 11, the big number 11. Remember, a lot of these are. Did I already pass it? No. Where's California's? Oh, it must be the end. Yes. Sorry. There we go. This will be the last. What are California's latest issues? Well, it was reported and I may not have all my reports straight chronologically. This is July 2014. California orders emergency shutdown of fracking wastewater injection sites over fears of contaminated aquifers. This is from now a lot of news agencies covered this in July of last year. These are direct quotes. Emergency shutdown, 11 oil and gas wells. injected in sites in Kern County earlier this month, fearing that there might be contamination. Again, that's fearing there might be contamination. Later on, there is some reports, some actual studies saying that there has been, but it was revealed that the California State Water Resources Board has sent a letter to the EPA confirming that at least 9 of those sites were in fact dumping wastewater contamination from frac fluids and other pollutants in the aquifers protected by the Safe Drinking Water Act. Well, when you inject produced waters into in California, again, remember these class 2 wells are the Safe Drinking Water Act protects various aquifers based on their concentrations or TDS values. I think it's 10,000 TDS and less protects them. There are some other criteria that doesn't come to mind, but there are certain ones that are protected. Well, the other ones that aren't protected, they're allowed to dispose of these produced waters into. But of the ones that are protected, there are ones that are called exemptions. Exemptions from the Safe Water Act. Now, what classifies as what allows you to be exempt? Because if you're exempt, then you can pump into these. You can put wastewater into it legally if you're exempt. Now, what would give you the idea that some of these would be exempt? Well, the process for calling these aquifers exempt was pretty fuzzy back in the day, according to what Dogger is saying, the Department of Oil and Gas Geothermal Resources. What they're saying is it wasn't regulated. It wasn't. What did they say? It was complex. There was a word that they used. That it wasn't clear of how you could become exempt. So for years and years, oil companies were disposing into these exempt aquifers. But what made them exempt was the question. So I'll come back to that in a second. So here was the letter from Dogger to the EPA, from Steve Bolin, the head. Complicating matters, 11 aquifers with historical injection activities before 1982 were described in state documents in the early 1980s as proposed for exemption. So in the early 80s, when this process wasn't really defined well, I'm guessing, or wasn't really looked into carefully, there were, according to them, state documents that said that these aquifers were exempt. Now there's a lot more attention to what becomes exempt and what isn't. And these 11 aquifers are not, should not be exempt. So there's this history that, according to what they say, these are direct quotes, that say that they should be, that they were exempt and that's why they did it. Now, are they covering their butts? I don't know. Question? Yeah.
I keep seeing 11 aquifers and hearing that number, but I'm not seeing the names of communities. What are the names of these aquifers? Like right. Who's affected here?
I don't have that information. So I don't know. It's in Kern County. I can't get more specific than that, unfortunately. But this is what they're saying, is that these 11 got through some process that happened in the 80s. And now things are getting updated. We're like, wait a minute, these should not be exempt. And you've been pumping into them for years. And then the press gets a hold of that. And now they're really looking into these. Now they're in question. These such exemptions are in question. So in addition to the zones of aquifers that are lacking exemption, these 11 have been historically treated as exempt will also be evaluated. So they're evaluating this. Somebody's evaluating this. Maybe they shouldn't be the ones evaluating it. I don't know. But they broke up the wells, and there's like 20,000 or 30,000 wells to cover now because of this exemption problem. 30,000 wells that they have to look at. They need to look at now to see how much they've been dumping into these non-exempt. More than 29,000, which are cyclic steam wells and hydrocarbon zones. Now they broke it up into 3 categories: Class 2 water disposal wells injecting into non-exempt, non-hydrocarbon bearing aquifers, or the 11 aquifers historically treated as exempt. So these are the Category 1 wells they're looking at right now, and that's what led them to shut off some wells. Category 2 is ones used for enhanced oil recovery into the non-exempt. And then this Class 3 is just ones that were not as important, but important nonetheless. The reviews of Category 2 and 3 is expected to be completed in early 2016. They've already done the Category 1. Let's see, so this is what they say. There are 2,500 wells on the Category 1 and 2 list. 140 of the active wells have been labeled for immediate review because they contain less than 3,000 TDS. So when they say immediate review, I'm not sure what that means. Does that mean they need to clean it up now? Probably not. It means they need to study it now to see what contamination, if any, has occurred because of this. So they're trying to focus their efforts. They're trying to cover their butts. They're trying to focus their efforts now. And with 30,000 wells, what do? This is their idea. So they're reviewing these wells for proximity to water wells and other risks of drinking water contamination. And this is their chart for Class 1 and 2, Category 1 and 2. So the number of wells in less than 3,000 milligrams TDS per liter, 176. 87 were into these, active ones are into these 11 exempt. And so it's 48. So basically, these are the numbers of wells that they're trying to look at now. And then later on, Category 3, they'll look at some of these others. So I'm
Todd?
yes.
While they're looking at these, they're not shut down.
No, they didn't. They shut down. What was the number? I forget.
21.
Yeah, they shut down. What's that?
Just 21.
Yeah, they shut down 21 wells.
So
even though they're
the
looking
other
at
2,000
right.
Yeah.
are still operating.
Yeah, I mean they're not. Some of them are idle. Some of them are produced. And I should mention, although the studies aren't really been reviewed, periodic, there is a where is it? A letter from the Center for Biological Diversity did their own quick analysis and suspected high levels of dangerous chemicals such as arsenic, unknown carcinogen, and thallium. Now, again, are these scientific studies that link before and after? No. They're examples. Now, actually, I've seen the data of this, the Excel spreadsheet that came with this. It's not entirely clear, but arsenic is the one thing that pops out, because they actually have data from the 90s and the 80s from water wells. And arsenic does peak up recently. So that there is something to that. But again, right now they're just Excel spreadsheets that are out there for the public to play around with. So, but again, it goes back to the lack of data, the huge data gap that's out there. Yes?
Todd, I just want to mention that, you mentioned earlier that, most of the chemicals that they're injecting into the injection wells are not toxic.
Right.
The ones that are really toxic, I'm not talking about the ones that you drink and you're going to drop over dead right now. Like hexavalent chromium 6, that's one of the things they use to keep things from corroding inside and stuff. You could drink a glass of that right now, and you're just fine. 3 or 4 years from now you might have cancer, but this stuff is there and it's not going to go away. And it's really bad for you and your family, and if you're a farmer and you water your crops with this stuff, all your crops die. It's bad stuff.
By the way, they do use treated wastewater for agriculture in Kern County.
Has to be diluted.
Has to be diluted, but they do use treated fracked wastewater. Not just fracked wastewater, but also a lot of the produced water that comes out of these. Sean?
Yeah, you said that recently they have for increase in arsenic in groundwater, and do you think that could be at all related to just overuse of water now or just lowering the constant, or lowering of the concentration?
Like lots of pumping going on. You know, that's something that would be looked at for sure. In the study in Texas, in the Barnett, when they looked at all that stuff, one of the possibilities they said it could have something to do, not just with fracking or maybe not fracking, it could have to do with the lowering of the water table. They did mention that. So maybe. Now, arsenic is natural too in a lot of Southern California soils, so that's where the scientific studies need to come in. And the lack of data is going to hurt it. Sure. Yes.
So Wild Goose storage facility has a class 2 injection well.
Yes.
How would we determine if they have an exempt aquifer that they're pumping into?
Well, they don't. They actually have a closed system. They pump. This is in Butte County. It's called Wild Goose Storage Facility, and they pipe in gas from different parts of the country and even in Canada too. They pipe in gas and they store it, and they store it in natural reservoirs that have been depleted. They used, because all the original gas is out, but now they use that pore space to pump down and store gas, and then they will produce it when they want to sell it, or sell to PG&E, sell to whomever. And when they produce that, they bring up water, natural waters. But that water goes right back into that same reservoir. It's not on the surface, it's not disposed of in treatment plants, it's a closed system, according to what they say. So,
no additives.
Right, it's a closed system.
To store it, they generate fairly high pressures.
Yes.
Is that true?
Yeah, but they do not want to frack. They are very clear about that. That would hurt them to frack. Yeah. So I wouldn't say very high pressures. When it comes to the storing, it's pressures, but it's not very high pressure.
Yeah, under that same report, volume 1, it states that in California, operators are fracking storage facility wells like about 30% of the time.
By accident or by?
No, on purpose, because it increases the volume so they can store more gas.
Capacity.
And that, according to that report you heard earlier, that data is in that summary.
Okay, I haven't seen that.
I can show it to you.
Okay. All right. Thank you very much for staying.